All right, so hello everyone. Welcome to our workshop today on machine learning and artificial intelligence. We're going to start off by making something quite clear, a very deep concept here. Oh, oops. Oh no. Oh my goodness. All right. Awkward slide. With that, we're going to just jump right into it.
That was a pretty good slide. Okay. Basically we're just gonna introduce machine learning, AI, different types of models, like regression models, classification models, the machine learning process, and neural networks and deep learning.
So I guess the first thing to start with is what exactly is artificial intelligence and machine learning? Well, there's this very important computer scientist by the name of Alan Turing, and he described artificial intelligence as the science and engineering of making intelligent machines. So this is a very cutting edge field of research in computer science, as you know, general intelligence is something that we're far away from, and it is the end goal sort of the artificial intelligence research field. And so there's a lot of very important applications for this in the world today. We could allow computers to do different kinds of things that humans see, and more importantly, learn on their own and be cognizant and intelligent. And within the very wide field of artificial intelligence, a subset of that is machine learning, which is leveraging data to build a program. So just to sort of make a distinction, AI is sort of the overarching concept of the field, whilst machine learning is just a subset type of artificial intelligence. And the way you have to think about machine learning specifically is that, well, it's almost like reverse programming. So if you ever have written a program, right, you start off maybe opening your code editor and you take some sample data and you write the program that way. And you get outputs based on what you have designed. Well, in machine learning, you sort of do the opposite of that. You take sample input data and you also give the machine learning algorithm or the model the outputs of what you want. And then it spits back out the program, which is kind of a weird thing to think about at first, but this sort of helps you understand the revolutionary way that machine learning applies, in that you don't have to program it. You sort of have to provide data to it and train the model that way.
Okay, so three types of models we have are machine learning: supervised, unsupervised, and reinforcement. So supervised is when you sort of have the outputs for like the classification for the data, and based on like the weights that you train for the data, like you're gonna have like feedback for that, and the model will like adapt accordingly to better fit the data. And unsupervised, you don't have the outputs or like feedback, any of that. Reinforcement is when you have this idea of rewards. So certain outcomes are seen as more like favorable than others, and you're sort of like just trying to like create series of actions that optimize the reward. And two types of problems are like classification and regression. So if you see the image on the right, the top one has like, or like the image of the 9, you're basically like taking an image and they're trying to classify the digit. So there are like 10 different classes for like the digits like 0 to 9, and basically what it's doing is it's like assigning a probability for every single class. So you could see that like this number is like a 0 with probability like 0.05, it's 1 with probability 0.01, and it's a 9 with probability 0.94. And then regression, on the other hand, like deals more with like continuous outputs. So based on the data, sort of like creates this equation, and So now you can like you can now like give it an input. So say like 400 square feet, and using the weights that in the model, like it will predict a price.
So we're gonna then just jump right into breaking down what exactly the first type of machine learning models we discussed, which was regression models.
Okay. So yeah, so one type of regression is linear regression, and this is basically like your typical like find the line of best fit given a bunch of data points. So for linear regression, the hypothesis function is represented as like b plus like w's to 1x, where like b is your bias and the w's are going to be your weights. And the point is to like create like a hypothesis function such that the loss function is minimized. In this case, in linear regression, the loss function is mean square error. So you're trying to minimize the mean square error. So I guess like in the image shown, you have an equation that the hypothesis function that's like just like one weight. You're given like 1x for it. So it's then like you're gonna have like one weight that's like multiplying the x, and so you're just gonna try to minimize that, but then the loss for that versus like that's one feature compared to like multiple features. So take for example, like say your input is a 2 by n matrix, so you have n data points, and like each like data point has like two features. So then you're gonna have like x1 and x2. So in that case, the hypothesis function would be like b plus like w sub 1 x sub 1 plus w sub 2 x sub 2. You have like different weights corresponding to like the different features.
Sorry about that. So you may be wondering, right? If you ever taken a basic statistics class with linear regression, I think you probably have all sort of mostly interacted by finding the line of best fit, either just by approximating it or just allowing the computer to find it for you. However, since we're trying to develop a model that is precise and accurate, we need an approach to ensure that, well, if we go back to the previous slide, that we minimize this loss function. And the approach we do that to sort of, instead of doing the just sort of picking random lines and try to figure out the best one, is we use an approach known as gradient descent. And so the way we do that is we take points along the desired graph, as shown sort of in this photo right here, and we take the gradient, or in two dimensions it'd be a derivative, but we take the gradient of that and adjust it based on the learning rate, which is alpha right here. And we use that to determine the adjusted weight afterwards. And so we can correct the model as we go. So as I mentioned before, in two variables, that's a simple gradient when you only have one output variable. But when you get into more complex curves and more complex machine learning models, maybe like this one here is where you have two predictor variables and one output variable. Then you need something more complex in order to determine the point along this gradient. The gradient, you need the gradient itself to determine the rate at which you're trying to adjust it. So just to get a better intuition of what this sort of looks like, we're going to look into this visualization tool right here. So we have this hypothesis function right here, and we're attempting to optimize it by putting it on the the minimum point right here, which would minimize the result of the cost function, or the cost slash loss function. So I'm going to simplify this a little bit by making this x squared, and we're going to adjust it. And we're setting the learning rate, which is alpha, by 0.25. And as you can sort of see, as we do linear like iterations of different potential models, we approach slowly where our eventual goal would be, which would be a completely flat line at y equals 0. And so, as you can sort of see, early on, the gradient allows us to adjust very quickly by larger scales on where we need to go. But as we come closer and closer, we want to become more precise. And so, as we continue the iterations, right, you want to sort of, that's the sort of idea behind machine learning. As you increase the iterations, your hope is that it becomes closer and a closer approximation of the value itself. As you can tell, if we try different iterations as well with the similar, that may have been too big of a step side. Learning rate, let's try to go something small. So if we reset and we get a slower learning rate, as you can see, in a similar sense, it approaches in the same way using gradient descent. And with that, that's sort of the intuition behind how we minimize the loss from, the equation itself, and also allow us to then determine a very accurate model. As you can probably tell, this is not the best model. This is purely a linear regression model. When you get into more complex variables, and especially after you take multivariate calculus and linear algebra, you'll be able to get a better intuition on how you may be able to do a multivariate model to map it and calculate complex loss functions from there. But for now, we're going to maintain this similar, very simple example.
Okay, now we're going to talk about some classification models.
So as we mentioned earlier, classification is when you want to sort of sort between discrete outputs. And the way you do that is mathematically. You do it slightly similar to linear regression in that you use logistic regression. What this means is that instead of finding an equation to find the relationship, you find something called a decision boundary. And what a decision boundary is, in itself, it is an equation that maps the outputs, that sort of divides the outputs into the separate groups so that it's able to identify the two separate groups. In this case, since we're using a linear model, we're going to have binary classification because we have a very simple linear model and we divide the graph into two. And once we have this sort of decision boundary, the way it sort of falls on where these outputs lie in between the binary classification is we have to use modeling using logistic regression, which is modeled by the sigmoid function right here. I think this is also very similar to the hyperbolic tangent, tan h, if that's something that will be better notation for what you find. But as you can tell, this acts very similar to linear regression in that, well, there are weights to particular features, and there's a bias to adjust from those weights and features being multiplied together. And this is applied all inside together as a cumulative sum before then the sigmoid function then applies. So in this example, if sort of it approaches up here, it is categorized in one group, while if it approaches down here, it's categorized in the other group.
All right, so we have activation functions, which are used to map continuous outputs to discrete outputs. So if you take, for example, say like a function, like a linear function, you can use an activation function to sort of like classify that. So take so specifically like talking about the sigmoid function, if you have a function like z, which is like a linear equation maybe, then you would be doing 1/1 plus e to the negative z for your function. And like as Benson said, that's sort of just gonna do like binary classification, classify it in like one of two things, because the sigmoid approaches 0 on one end and 1 on the other. And so like 0.5 is sort of like the line between the two. Then if you want to classify it in more than one way, you have to use softmax function sort of uses like probabilities to classify things. So basically, like if you take that function z again, it's gonna do like e to the z sub I over the sum of like all of the e to the z values, and like assign that ith class a certain probability for like whatever you're trying to classify. And there are other activation functions. That's so like the slide just shows like a bunch of them. One in particular, I guess, like ReLU, which takes the max of 0 and like your input. So all values like greater than 0 will be like the input itself, and everything else would just be 0.
So we're going to delve into a little bit the machine learning process, how exactly you sort of construct a machine learning model, and the data collection as well.
Okay, so there are several steps in the machine learning process. So you start with like collecting your data, and this depends on like, what you're trying to classify. So say like if you take, maybe you're trying to classify like, I don't know, like you like dice, and maybe like images of dice, and you're trying to say like, okay, like this is a 1, this is a 2, like so on. So in that case, you would want like images. But then if you take, for example, like, I don't know, gas prices, then that's like numerical data. So in that case, you want like numbers rather than images, and also like the way in which you go about like collecting the data. There might be like certain like biases and stuff. So you just want to make sure that you're accounting for that when you're in the way that you're collecting the data. And then afterwards, you're gonna do like pre-processing, which is just like removing like unnecessary stuff. So you have like an image, maybe like outside like noise or something, you know, stuff that's like sort of like localized to like, I guess like on the side shows like a picture of a cat. Like you want to like say like, okay, this is like the cat that, you know, like just yeah, just remove like the background, the excess background stuff. And then you're gonna train your data. So that's basically just like building a model based on like the data. And then you're going to test the model using like different like validation data. And you're just gonna see like how well your model performs on that. And so if there's like a lot of error using your model, then maybe you want to like adjust your model a little bit compared to like if there's like little error like on your validation data, then it might be like a pretty good model.
So to talk a little bit about data collection and some issues with modeling. So as you can see up here in the right-hand corner, this is a great visualization to determine how you subset your data. So if you think about it, right, after you collect your data, you know, a gut intuition may be that you want to use all of your data to train it and it becomes really good. However, this is not the best way to do it. A typical standard is that you do an 80-20 split between training and testing data. And the reason you do this is because you need some way to prove the accuracy and verification of your model. So while you want to spend a majority of your data, 80% of your data is a good number, to test and to train your model, you also want to provide about 20% so you can ensure that the model is actually general enough and that it actually applies well to the context you're working on. And just to make a quick distinction, this diagram, this makes a distinction between training, validation, and testing. Validation data specifically is that the data you repurpose in your training to sort of provide feedback to your model to improve over iterations or epochs of your training, while testing data is what's sort of your final determination of how accurate your model is. And there's one question that is often very confusing to people starting off with machine learning, and it's the idea that, well, 90+% accuracy is not always good for your model, because this could be caused by something called overfitting. It could be that your model is really good, but it also could be overfitting, which is always something you need to analyze as well. And the difference, as we're going to talk about overfitting, underfitting, is that overfitting is that your model is not generalized enough to the data, while underfitting is that your model is too generalized. So first, we have underfitting right here. As you can see, the data between, we want to classify the X's and O's, and we have a linear model right here. This is too generalized. This is not very good. It accounts, there are a lot of outliers here and there that it does not account for, and well, that's not a very robust model. But then the other problem is we have overfitting here, in that it only matches the data set perfectly. Like if this is like analogous to you as a student, if you're coding a project and you only write test cases to match the data, you don't write a proper generalized solution. And so because of that, this is not a good solution you want to have either. You want to have an appropriately fitted model, which is shown right here, which accounts for a majority of the data and is generalized enough that, well, it will apply pretty good to the testing data as well.
Okay, so going along more with like the idea of overfitting, how do you prevent overfitting? So you could see like the line, I guess in the picture, the blue line seems to like hit all the points. So it has like zero error, but is this like very like complicated like shape it has, and it's like very complex. So it's pretty like good chance that it's gonna have high testing error. This is definitely overfitting the data. So you can prevent overfitting by using a regularization term, which is basically a term that's like the term in like the red box, for example, which is like added to the end of a loss function. And so using the regularization term, you can obtain something more like the green line, which is a lot more generalized and is more likely to better fit testing data. And this regularization term is also like only used when training. So this does not exist when you're like testing the data using the model.
So now we're going to jump into sort of an interesting core crux of machine learning and AI, and it's the cutting edge research of neural networks and deep learning.
Okay, so neural networks are sort of modeled after neurons in the brain. So basically like trying to like you can use like a combination of like different functions to better model like a larger variety of data. So take for example like logistic regression. The first step in logistic regression is sort of like using this linear function. So you could see the part within the sigma says like wx plus b. It's like linear. And if you look at the top image, you see like a bunch of different arrows. And if you take like the first like circle in the like first blue rectangle, for example, like you could see that each of the red like the inputs they each have an arrow pointing to that circle, and like they each have an arrow pointing to like every like circle like after that. So basically like each of these arrows correspond to different weights, and so to get like each of those like four values, you're gonna do like, so say like the three arrows pointing to the like the first circle are like the they correspond to like W sub 1, W sub 2, and W sub 3. You're gonna do like W sub 1 x1 sub plus W sub 2, x2 plus W sub 3, x3. And then each of these circles, so these arrows are not shown, but each of these also have an additional arrow, which is like the bias term. So that's sort of just like the B that's added to the end. And so that's how you're gonna obtain each of those values. And so logistic regression, like the linear function is the hidden layer. And then to go from that hidden layer to the output layer, you're gonna want to use an activation function. So in this case, the activation function would be like a sigmoid function. And so that would be like, so if you say like the values you got were like Z, it would be like 1 over like 1 plus e to the negative Z. And yeah, so you just go from using that sigmoid function to get your output and like classify the data. And you can also just use like a combination of other functions, like different like functions, like hidden layers, like different activation functions. That just allows you to like better classify the data.
And just to sort of build off the basis to more complex, deeper neural networks, as Lasya talked about on the last slide, the fundamental unit is this sort of like artificial neuron, which is conceived by a bunch of different regression classification problems depending on it. And these subsets neurons, these like nodes, then form together into this fundamental unit in this upper right-hand diagram, and that you form a bunch of neurons together and combine them into a perceptron, which is this whole unit right here. And these perceptrons form a layer of the neural net, and this allows you to more accurately combine features in context for one another and weight them specifically so that you have a particular node understanding a lot of different features in context, which is more robust than a simple multivariate model. And so when you do this, well, then you have combine this into another fundamental unit, which is a single layer neural network. As you can see right here, you have one hidden layer of perceptrons forming together to add to another layer of this neural network. And these hidden layers map the different input values to the different neurons and nodes here, sorry, to form these perceptrons. And overall, it outputs the fundamental output based on there. To sort of visualize this intuition a little bit better, I'll be showing this quick visualization. So this is a pretty cool website. This is developed by TensorFlow, which is a very popular machine learning library in Python. So as you can see right here, you have several. You have a model right here with a set of input layers, and then you map it to a set of one layer of neurons here, and map another layer of neurons, and you produce the particular output model right here as a set of data. Well, if we want to say add more neurons, then we can see that the complexity increases as we go along. If we then want to add more layers to form more perceptrons, then it also increases the complexity as we go along there. And so there is a lot of different things you can weigh as you go along. As you allow, one of the core concepts behind neural nets is this idea of backpropagation, and which, as most neural nets are feed-forward neural networks, which produce these outputs in the manner we've been discussing. So backpropagation forward takes the output of data and feeds it back into the network. And so as you can see over time, it forms a pretty good classification model here, if you do ask me myself. And so as you can see, as this sort of the nets sort of form as we go along, in increasing epochs, it gets better and better. As you can see right here, it's actually already really good with a training and test loss of 0, which is amazing. But as we see as we go along, there's some bit of error right here. But I'll pause it right here, and we have a really robust model right here. So with that, I'm then want to just highlight couple resources we put on here. And as there are many different applications of neural nets, I do want to highlight this learning lab real quick, which discusses convolutional neural networks, which is related to images. And so as Lasya talked about earlier, there's sort of a process of handling things. So in neural nets with computer vision and images, you deal with convolutions, which if you can sort of get the intuition from right here, it's sort of like moving across the frame of the screen to analyze a very small subset of what the overall image is in a particular context. And then when you focus on this context, you be like, okay, wait a minute. So, there's a nice fluffy ear right here. There's a nice soft head right here. There's a fluffy ear right here. There's a nose right here, and there's some paws. It's on a tree right here. And then maybe the model is then able to classify, well, based on these particular convolutions and these particular contexts and their weights together, well, it gains an overall understanding from the neural net that, well, it's a koala we have right here. So I definitely recommend exploring CNNs if that's something you're interested. But with that, that's the general content we have ready to cover. We're going to stop the recording now and we'll open it up to questions if you guys have any.